because they just spent like $6 million.
So, what do you think would be different about this? Talk about a smooth transition back into the class. What do you think would be different about this here problem? Kind of something very obvious. One level is not different at all. It's just that you've got to realize that there aren't just zeros involved here. There are places where it's undefined. And just to show you an example, we've seen an example where we're talking about asymptotes, right? Some of you showed me. That's not negative. So let's say there was an asymptote right here. It has a slam up against it, right? Remember that? And then it could maybe do this. On one side of this asymptote, the function is positive. On the other side, the function is so it could change signs around asymptotes also, right? How are we doing?
Sure.
Because you can see it right there. So where could it change sign? It could change sign at the zeros. What are the zeros?
1 and 0.
I like it. And where are the undefined positions? There's only one, 4, right? So when you make your little number line, what do we normally put above the important points? Put little z's for 0. What do you think I'm going to put above 4? A little u for undefined. So then I know that that can never be part of my answer. If there's a little u on top of that bad boy, that can never be part of my answer because it makes it undefined. It's automatically thrown out. My little z's tell me that's where it's 0, and in this case, I want to include those positions, right? So when I draw this little number line, it feels exactly the same, except when I have, here's my -7, 1, 4. I got a 0 here and a 0 here and a u for undefined there. So I know that 4 better have a freaking parenthesis on it. I can never include that 4. Makes it undefined. Then the work's the same. You're still investigating the sign of this thing. So for example, if I make it 0, if x is 0, what do I get here? I get a negative times positive divided by negative. So the overall is going to be positive. Let's do this one all the way out and see if our shortcut from before still works. What about if I plug in 2? Yeah, so I get positive times positive over negative. So I get negative. If I plug in a 5, 5 minus 1 is a positive number. 5 plus 7 is positive. 5 minus 4 is positive, so I get positive. Cool? And the last one I left out was a -8, maybe. Throw a -8 in, I get negative, negative, negative. Negative is negative, positive, I have a negative is negative. So did it do like we thought it should for that shortcut I was talking about earlier? Yes. The shortcut still works here. It's awesome. They are all to a first power. It should change signs around each one of them. So I really didn't have to do all this work then. Right? Just had to find one of them and they just change the signs all over the place. So what's the answer to this question then? So where is it? Negative or 0? So it's negative from negative infinity up to -7. Do I include this -7?
Yes.
Yes, because I want to equal 0. Or between 1 and 4. Do I include the 1?
Yes.
Do I include the 4?
No.
Hell no. because it's undefined there. Never include that no matter what. So it's the same stupid problem, right?
Essentially.
Essentially, yeah, because it can only change signs if it goes through the x-axis. Because otherwise, if it doesn't have to go through the x-axis to change signs, it just goes, oh, I don't like it up here anymore. Oh, how the hell does it do that? Polynomials are nice. Polynomials are connected. They have to stay connected. It's something called continuous. You can't lift up your marker to make them. In pre-calculus, and we've already seen several, where you have some functions that do jump around. And you have functions that jump around like crazy. The only other function we know that jumps around, this isn't really a polynomial here, right? Because it has a variable on the bottom. But the nice thing is it says, okay, you can only change sign if you go through the x-axis or if you have a wall somewhere. Cool? Can somebody tell me this? What would I change on this if I didn't want it to change signs around the 4? See how it changes signs around the 4 right now? If I didn't want it to change signs around the 4, how would I change this equation? Put a square on there, right? So it follows that rule, just like it did when it was in a straight line. It follows the same rule. Okay, I want to, oh, go ahead.
Wait, what?
So remember, what was the rule from before?
The square, but now if you...
So if I put a square here, right, if I had this,
undefined,
it stays undefined, hell yeah.
but it makes it
Let's
positive.
investigate this.
Okay.
Right. Real quick. I have all the same points I did before. It's still 0 here, 0 there, and undefined there.
Okay.
But now when I put in like -8, I get negative. Come on, Jeff, you can do it. Times negative over positive. That's always going to be positive now, right? So that's going to be, why did I put negative? Positive. If I put in 0, I get negative times positive over positive. I get negative. So far it's doing like it should. It changed signs around that one. It should. When I plug in 2, I get positive times positive over positive. I get positive. Cool. So I changed signs there. And then when I plug in 5, I'll get positive times positive over positive, and it's still positive on that side.
Okay.
So it still follows the same rule. So again, I didn't have to do all that work. I just want to show you that it does work. I can identify the places where it's to a positive power, and whatever it is on one side is going to be the same on the other. And the everywhere is to an odd power. What did I say? Positive. An even power, it's that. Odd powers is going to change sign around there. Right? So to do one very quickly, if I had like that. That's crazy.
That is crazy.
What do I put on my number line?
5. -5.
So -5,
-4.
-4,
and 7.
and 7. What goes over the -5?
Z.
Z, because that's a 0 of the function, right? These two are where it's undefined. Now here I kind of purposely did something. I can't pick a nice whole number in between, but I know the shortcut now. If I had to check this region out, I'd have to use -4.5 or something, right? Something gross. But since I know the shortcut, I could just pick the number 0. When I plug a 0 in, I get positive, negative, positive. So I get negative for 0, right?
Mm-hmm.
Is that cool? Now where's it going to change sign? Does it change sign around the 7?
No.
Sure.
Oh,
Positive.
yeah.
It's to an odd power, so it better change sign there, right? So odd powers, change sign. Wow, Jeff. What language is that in? All right, let me start this again. Okay, so odd powers. Yeah, Jeff. Change sign. Okay, that looks roughly the same. Human powers. Stay the same. If you really think about it, if that 8th power wasn't there, around -4 at -5, this would be negative. At At negative 3, this would be positive, right? But by having that even power on it, it makes it the same sign on both sides. It makes it always positive then, right? That's why the shortcut makes sense. So all I got to do, and normally I just try to plug 0 in if I can, right? Or 1 or something easy. And once I get that one region, at 7 it should change signs because it's an odd power. So it's positive up there. In here, which is around negative 4, it should stay the same. And around negative 5, it should stay the same. Do you see that? And if you don't want, you can always plug stuff in from each region. There's nothing wrong with that. This is a shortcut. So if you still wanted to, let's change it. God, I'm not sure what language I'm writing and what language I'm speaking. If you put an 8 in there, you get positive, 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 positive. Right? So what's the answer to this question then? Or is it greater than 0?
From 7.
Yeah, you definitely don't include 7, right? Cool. Now, here's the evil part. If I would have said blah, 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 greater than or equal to 0, the answer would have been 7 to infinity, but you'd have to include something a little weird. That's the only place it's positive, right? But if I would have said greater than or equal to, where else is it equal to 0? Negative 5. That's probably the weirdest answer you would see when I'm asking you where is it equal to 0, and it's the same sign on both sides. You might have to only include that one point. At negative 5, this is 0.
Ouch.
Okay, maybe. All right. So if you don't like the shortcut, you don't have to use it. You never have to use any shortcuts I show you. There's always a long cut. And the long cut would be just check each region out. Here we're kind of discussing, but too bad. So the reason people have trouble with this section, and I want to really directly address this, is we're not actually solving this equation or inequality in any way we've ever done before. Before we would solve it by cases, some direct algebra, right? Here we're doing it visually, which is really the point of algebra. Algebra says you can solve equations visually, like we did with systems of equations. What was the first way we learned to do that? Visually. We didn't do any algebra. We just graph one line, graph the other line, saw where they met. That's the visual way to get the answer. So to do this problem, I could do a lot of cases that would suck so bad. So screw that. Let me do it visually. Let me see where is it negative, where is it positive, and I can answer the question very quickly. Okay. All right. You guys look very excited. I don't blame. Let's see. Sure, you guys try this one. So, what's going on here? What are our zeros?
Negative 7 and 1.
Cool. And it's undefined at 0. Alright, so when you, let's see if we can do this short. If you put in 2, just pick a nice number to use. You can't pick 0, of course. You get positive, positive, positive. Will it change signs around the 1?
No.
Because it's to an even power, right? If you don't like that, you can always plug in a 1/2, and you'll see that it will be positive. But the shortcut is, since that came from a factor with a square, with an even power, it's going to stay the same sign on either side. It's going to touch it there, right? What about around 0? Will it change signs?
No.
What power is it to? And that's an odd power, so it should change signs.
Oh.
And again, you can check it by plugging in a -1 in. You get positive times positive over negative is negative. Will it change signs around the -7? Yes, because it's to an even odd power. Changes signs. Again, you can plug in -8 to check it. Right.
So if we understand the shortcut, that's all we need.
Yeah, the shortcut's awesome. Right. So you can just show me a little work for the first point you do, and then you just fill it in, knowing what you know about the powers. Right. What's the answer then? Do I include it? Yes. Or
Not including 0.
yeah, not including 0 up to infinity. I like because you're going to include this 1. You don't have to stop at 1 because it's included from 0 up to infinity. It's positive or 0, so that's beautiful. I like it. All right. So real quick, this one's probably a better graph to look at. I want to try to show you this graph so you can see it's doing what we said it should do. First, I have to cover this board with that. Yeah, it just freaks out there. Supposed to be. Alright, so I use such high powers on there, I wouldn't even think I want to try to graph it, but you can at least see it's negative. It's really small negative here, that's why you can't see it, but it's negative all the way through here. It hits 0 at those 2 places, right, like we said it should. It's undefined at -4, which is a little bit hard to see because I think it jumps from -4, but it's still negative because it comes back up here. That's where we can't see it too well. It's supposed to be undefined at 7 and then become positive after 7, right? So if I zoom in on that, it's not the best thing to use for an example. Oh god. Alright, enter. Come on. Yeah. So there, it's negative back here, and it's undefined, and see now it's positive up here, right? You see that? Isn't that what's supposed to be negative? Undefined, positive, right? So you can do the same thing for the last one we just did that's underneath here. You plug it in the calculator. You got to be real careful. Notice how you have to be really careful when you plug it in. That's the top, and then parenthesis x minus 7, parenthesis x plus 4, close parenthesis. You got to put parentheses around the whole bottom here to tell it that the whole thing's on the bottom. Right? That's if you wanted to graph this thing. Okay. Pretty disgusting graph. All right. You do the same thing with this if you wanted to, and you should see it doing this. It should be positive here, go through, become negative, undefined here, so it probably does this kind of thing. So it's positive, goes through at -7, so it's negative, undefined at 0. It's going to It comes up here, so it's positive over here, right? It touches 1. Poor 1. Feels so violent. And then it's still positive afterwards, right? So if you graph that, it should look, very roughly like that. Very roughly. Right? So if you want to try to graph it, see what it does, that's what it should do. Okay. That's all there is in 8-9. I want to adjust the homework just a little tiny bit. So for 8-9, just do, I think it's 9 through 24 every third one. Just do those. There are some other ones after that, but just do those. Yay. So section 8-9 homework has been adjusted a little bit. Just do 9 through 24.
And our quiz tomorrow is only on 8-5 and 8-6.
8-5, 8-6. Okay. Wow. Every day is chock full of stuff. So I'm going to do at least 1.5 sections out of 9, and then we'll head out. All right.
Does that mean we're going to have a quiz on, well, no, never mind.
Okay. No. Because notice, when's our next test?
Tuesday.
Tuesday. So tomorrow I'm going to have a practice test for you. Monday is going to be mostly review. There will be a little bit of new stuff. And then Tuesday's the test. Wednesday's review for the final. Thursday's the final. So next week is hell week. So be ready. Test final. Okay. All right. So one nice thing about section 9.1 is that it brings back something we know from before. It's not so nice if you really hate functions, and I know there's a few of you guys who are in that boat. But we've already kind of done this. We've already done the first part of section 9.1. It's called composition of functions, which sounds scary, possibly, I don't know.
A little bit.
But all that really means is, let me start this off. This isn't fully this thing, so I'll say recall. If I have f of x equals 2x minus 4, what is f of a plus 3?
Okay. 2 times.
Yeah, you just take this and plug it in there, right? So it'll be 2a plus 6 minus 4, so plus 2. How's that? Cool? Right.
Oh, okay.
So we've already done examples where we put expressions into functions. So the only thing this section says is, let me actually, before I get to the full new stuff, what would f of 2x plus 5 be? Let me see if you guys don't get too turned around with this. You do exactly what you just did. What do you do with 2x plus 5? You plug it in there, right? So it'll be 2 times 2x plus 5 minus 4. So it's got to be twice the thing minus 4. Twice the thing minus 4. There you go, right? It's just plug and chug. So what do you get there? You get 4x plus 10 minus 4, which is plus 6. Cool. Not a big deal. So, why is it a problem? You can tell I probably have had issues with this in the past. Why is it a big deal if I say, okay, what if f of x is 2x minus 4? G of x is, oh, I don't know, 2x plus 5. I'd be a real dork today, excuse me. What is f of g of x?
The same thing as that.
It's the same stupid thing, right? What's g of x?
2 plus 4.
Yeah, so you first, and what do you normally do when you have to simplify an expression? Don't you start inside parentheses? So what's inside the parentheses? G of x. Alright, what's g of x? 2x plus 5. And then you just do everything we just did over there. Right? So we've already plugged expressions into functions. And couldn't an expression itself be a function? So we've already plugged functions into other functions, right? We just maybe didn't use this notation before. Just to warn you guys, the full true notation for this is, it's kind of funny. And it's really unfortunate, right? Remember how this notation, what did this notation really mean? Who remembers that? Exactly, f of x plus g of x. So this notation, it's a little weird. What the hell does a circle all of a sudden mean? And some students love it because it's the fog function. That's what I feel like I'm in. But this just means f of g of x. Of g of x. So that's the way to immediately rewrite this weird-ass thing. You write it like we're used to, right? Not really sure why we had to make a whole new symbol for it. That's too bad for us.
We wanted to confuse the rest of the population.
Cool. So let me throw a little weirdness your way. What about this here?
What is it? Hey Jeff,
Yeah.
the bottom line, after the second f, what does it say? F of x plus g of x.
Yep. Exactly.
Okay.
So what if h of x is 2x squared minus 7? What is h of x?
So you would do 2.
What's the first way you could rewrite that to look a little better than, oh. So what are you plugging into h? Don't worry. Itself, right?
Yeah.
So,
Can you write that as an example? Because I'm trying to see where the parentheses would be. For example, like the first one.
how do you mean?
You're plugging in that equation?
Yeah. Because it's just, how do you rewrite this symbol? How do you rewrite this symbol? Like this. So that's the first thing I did, which is that symbol really means that. It's like a shorthand for of, h of h. So h of h.
So it would be 2.
So starting inside, what is h of x? X squared minus 7. And then you have to take this whole thing and plug it where?
Into the x.
Into h, yeah, into the x there.
Oh, okay, see.
So then it would be 2 parentheses 2x squared
I like
minus 7.
So what does h do to anything? It does twice that thing squared minus 7. So what's that thing we're talking about now? This.
Okay, so that's what I wanted to visualize.
Good.
Okay.
Yeah, just the next few steps. To simplify that, you'd have to square that out, FOIL it, double it, subtract 7. And, that should be easy after this, the cleanup stage. So you would twice, you FOIL this thing, you get 4x4 minus 14 is minus 28 plus 49. Double it, subtract, that should be the easy step. Should be. All right, it's just foiling and getting like terms together, what to do. All right. The weird step is this one. And I know it gets weird when you plug something into itself, but it's sort of like what's feedback? Where are my musicians at again? What's feedback? Or feedback, everybody knows feedback is when you get something back from somebody else, but it's when a sound you make and then the sound of the speakers gets fed back into the mic and then it's kind of a loop. So it feeds its own output back into itself. Isn't that exactly what the hell that's saying? Feed this back into itself, right? So we have a physical interpretation of what that is. I don't know. It's another good example. I don't know. I thought that was pretty good. Yeah.
Where's number 2 come from?
Which one?
Number 2.
This 2?
Yeah.
What does h do to anything? It takes twice that thing squared minus 7. Right? Isn't that what that says? What does h do to x? It squares it, doubles it, subtracts 7. So whatever's in here, if it was a, it would be twice a squared minus 7. What is it that we want? We want this. So it's going to take twice that thing squared minus 7. So the 2 comes from the definition of what h is. It better be there because that's what h does. Right? It doubles the square of that. So if I have again, if I have h of x is 2x squared minus 7, what's h of w? What's h of w?
2w squared minus 7.
Yeah, because what do you do with the w? Plug it in, right? So 2w squared minus 7. Where is that? Why is that 2 there? Because it's there. So no matter what I put, what's h of x minus 3? 2 times x minus 3 squared minus 7, right? H of anything, 2x squared minus 7. Would that be twice that thing squared minus 7? Because that's what it says to do, right? Okay. Wait. Okay. Let's see. If I had, this is not going to get gross, it's just leading us into something, here we go. What's f of g of x in this case? Yeah, square root of x was 7. What would you say if I said what's the inside function? What would you say that is? There's this whole function, but what's the inside function? G, right? And you can see it here, that's inside the f, and you can see it here, that's inside the square root. Right? So, if I, sorry, flashbacks of the fugitive. Set up a perimeter. We have. Right. If I have h of x equals 3x plus 8 cubed, can you guys tell me what is the inside function? Yeah, that could be one interpretation. That's the easiest one to see. That's 3x plus 8 is inside function. And what's the outside function? Cubing something, right? So I can kind of go backwards. What must have been g of x then? What is g of x by itself to create this? Yeah, what's the inside function? It must have been this.
3x plus 8.
Now what function was that plugged into? Yeah, x cubed. If I plug that into that, I get this, don't I? So it's sort of like thinking backwards. Normally they give us functions and we put them together. There is one section of homework that says, okay, here's the end result. Can you tell me what the inside, what g must have been, and what was it plugged into? So you kind of break it back up. You decompose it, right? This is the composition of functions. This is the decomposition. Oh, shit. Right. It's not that big of a deal. Hopefully you guys see that. They could get ugly, but they're not going to make them ugly. Right, so another example would be if I had this like that.
Can I ask you a question?
Yeah, sure.
I'm sorry, I walked in like at the end of this one over here. Where'd you get the cube from?
Here?
Yeah.
Okay, isn't there a cube in here?
I didn't see that.
Okay, so this is kind of like me trying to take this and break it apart.
Okay.
Break it up into an inside function, which would be g. And what's g inside of? A cubing function. Cool. What about over here? What would you say the inside function is over there?
4x minus 2.
So g of x would have to be 4x minus 2. Now, what function is that inside of? Here's the really cool thing. Once you identify this, replace it with an x. That's the outside function. That's what it was plugged into. It's plugged into 7 over the square root of something. If I plug this into there, don't I get this? You guys see that? Once you identify the inside function, you can just make it an x, and you're done. You're good to go. You could have said the inside function was square root of 4x minus 2, right? The whole other answer would have been g of x is square root of 4x minus 2. And then it would have been in the function 7 over x. Aren't they both valid answers, right? So in that section of the homework, there are several possible answers. Several possible correct and a million incorrect, so be careful. So I really desperately want you to see how this section, the only new thing really is like breaking it back up. We've never done that before. We have already done a lot of putting stuff into something else. Yeah?
Does that mean that g of x can also be just the 7 or just the 4 or just the 2?
Not really. Because if g of x is 7 and f of x, what would f of x then be? X over the square root of, but then this isn't 7, is it? Do you see that? Yeah. So it really has to have that form. The inside's got to be in something, and the outside's got to have the same form as this. See how it either has this form of 7 over the square root of something, or 7 over something, so they can recapture this form. Cool.
So find the variable and then you could.
Yeah, find the variable and see what the expression is, and call that one the inside, and then replace that with an x, and that's the outside. And there's a couple different ways to do it sometimes, yeah. So that section would be, where'd it go? Oh, there it is. Bottom of page 711, starting at number 31. Cool. So it shouldn't be too evil. So if I had square root of 2x minus 7 plus 5, what would the inside function be? All right, sure. Square root of 2x minus 7, sure. And what would the outside function be? X plus 5. Or you could have said the inside was just 2x minus 7, and then the outside would have been square root of x plus 5, right? So again, it's basically the same two options we had there, but there's other situations where you have more than one option. Okay, because math, you got to be able to go both ways. If you can put things together, you should be able to take them back apart. Okay? Blah, 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 blah. Okay. So here's the, so that's nice. And that's a good skill to have, especially for those of you going on to calculus. It's gonna rule your life knowing what's the inside function, what's the outside function. Because if you don't know it, you can't attack the problem. For the rest of you, just gotta be able to do it for me. The real big part of this section 9.1 is something called inverse functions. And we already know several inverse functions. We've been using them since the first time you did any algebra ever. What's the inverse function for something that adds 3? What's your gut tell you? Because inverse is another word for opposite, right? So if I have a function f of x equals x plus 3, the inverse of f, which unfortunately the symbol looks like a -1 power. That's just too bad. It's not, it doesn't mean reciprocal. It means the function that does the opposite thing, right? The inverse of f, the symbol for which is f inverse of x. But when you see that, you might automatically think 1 over f. No. The symbol means the function that does the opposite of what this function does.
So wouldn't it be -1 times x plus 1? Nope.
Don't overdo it. What's the function that does the opposite of adding 3 to something? It subtracts 3 from something, right? The inverse function must undo what this guy does. So look real quick at this. This is a really nice example to do this with. What's f of 7?
7 plus 3.
7 plus 3. 10. Awesome. What must f inverse of 10 be? Careful. No? So whatever f does to something, f inverse should undo that thing. Right? In fact, let's just do it. What do we get? F inverse is 7?
7 minus 3.
-7.
I'm sorry, not 7. I'm sorry. F inverse of 10. My bad. It should take what the other guy did and get it back to where it was. And does it? Yes. So think about that. If I have one guy stacking barrels, and then I had to say the next guy comes in the afternoon and say, okay, could you take those barrels down and put them out? Then it end up looking at the same thing as it did in the morning. And those guys are like, what the hell is that all about? It's like, I just don't like you guys. Right, so this guy, F, does work to this. It adds 3. I always think about like, one example for me would be like taffy. This guy pulls it out, adds 3 feet on the length of this taffy, right? You guys ever had taffy? I'm a southern boy, so taffy's kind of... So it takes a 7-foot thing of taffy and makes it 10 foot long, right? And then this guy says, I'm going to chop 3 feet off. And so it takes it right back to 7 feet long. You guys kind of with me? A little bit? Don't get in the whole, the density is different, all this shit. It's still the same. It's the same length it used to be, right? So whatever this guy does, this guy must undo. So that's really interesting. What point does this guy go through? What one point that we've done work for does this guy go through? F of x goes through what point? Careful. What work have we done that relates to F? What does F go through? What's the only thing we did with F? We put a 7 in, and the output was 10. So F of x goes through the point 7, 10. Now it goes through a lot more points, but that's the only one I know, right? What point does F inverse go through? God, I cannot write. What's different than that?
10-7.
10-7. Won't that be true always? If F goes through 2-5, F inverse has got to go through 5-2. Why? Because F inverse will take the output of F and bring it back to what it was. So if F goes from 2 to 5, F inverse must go from 5 to 2. It's really kick-ass. It's just a mirror image, right? Okay, maybe. Stay with me now. So let's let me see, I'm trying to figure out which way to go with this. Let's see how to algebraically find the inverse of something, because functions are not always as easy as, well, if one's plus and one's minus. There's normally a lot more stuff going on, right? So how do I find the inverse? So if I have a function, f of x equals 2x minus 5. I'm going to do this 2 different ways. One way to find the inverse, at least visually, is to do what we just did. Right? Somebody tell me, and you're all like, what did we just do? Tell me what you know about this line. What do you know about this line here?
Intercepts at -5.
Cool. The y-intercept is -5.
And the slope is up 2 over 1.
So up 2 over 1, up 2 over 1, up 2 over 1, right? Wow. That's really off. Oh, there we go. Looking at it sideways. Okay. Still off. Let's do after me.
It looks like it's clearer in mine.
It almost looks like your shirt.
Alright. Leave my port line alone. We all know it's supposed to be straight. Now, so what points are these? This is the point 0, -5.
2, 1, 1, -3. And 2, 1.
Yeah, and my scale sucks. That's why it came out so curvy.
But that's just 2, 1, right?
3, 1, right?
3, 1.
How we doing? Is that cool?
Sure, whatever.
I'm confused. How many did you go up?
Up 2
2
over
over
1.
okay.
Yeah. Cool. You can see that up when y goes up by 2, x goes up by 1. 2, 1, 2, 1. Okay. Just trying to get over my ugly picture. But okay. So what points should the inverse go through? if my f goes through the points 3, 1, 2, -1, 1, -3, 0, -5, what point should f inverse go through? 1, 3. Right? Because of the fact that we know that whatever this did to 3, it made 3, 1, f inverse is going to come back and say, change 1 back to 3. This guy's going to come in the next thing and go, what the hell? So what's it going to look like then? Let's graph the points. 1, 3, -1, 2, -3, 1. Oh, you can do it, Jeff. There you go. -5, 0. And then we'd keep going, of course. Now, do you guys see, this is not the best, I want to do like the cube root function, but that takes a little while to graph by hand. But, do you guys see how these are mirror images of each other around a certain line? Around the line y equals x? And why should that make sense? Because what do we do from one to the other? We switch the x and the y. So they should switch over the y equals x line. That's where the mirror is. Sort of like we had with parabolas, they have an axis of symmetry. For inverse functions, they are symmetrical around this line here. Okay, so that's how to find the inverse of a function graphically. Here's the cool thing. We're going to do it algebraically, and I'm going to show you it is this line. What's the slope of this line? Let's see if we can see that from my ugly picture here. It goes up 1 over 2. Cool? Which is sort of making sense. It's 1/2 instead of 2, right? Okay. So, and think about this. This function multiplies by 2, subtracts 5. So the inverse should divide by 2, or multiply by 1/2, and add 5 somewhere, right? You got to be careful. You can't just go from one to the other thinking like that. You don't know what order it does it in. So let's see, how do I do it algebraically then? Now, I think we've done enough of this, and it sounds like most of you guys, everybody kind of get this, what we did here. And I love to give you a problem where I give you a graph and I just have some points. You just make a list of all the opposite points and graph them, and there it is. There's the inverse function. That's beautiful. I love it.
F of x equals 1/2 x plus 5?
Careful. What I was saying earlier is you can't just guess at it. You know enough that it'll make sense when you get it, but some functions it's really difficult to tell what order it's going to do those things in. Right? So I brought the y back in. Because, remind me, what did we do with these points? We switched the x and y. So what do we do algebraically? We switch the x and y. If I then resolve for y, now think about it. If I resolve for y, am I not going to do all the opposite operations to solve for it? So it only makes sense that it should be the opposite function at the end. So how do I solve for y there? Add 5. Divide by 2. So I'm going to stop right here for a second. So it does everything we said. It divides by 2 instead of multiplies. It adds 5 instead of subtracts. But see how it's up here instead of on the side like we thought it might be? So you got to be careful about that, right? Some of you guys might be able to notice it does everything opposite functions in the opposite order. But even then, some functions are weird. You got to be careful. You really want to do this work to keep it straight. Break this back up into 1/2 x, a 1/2 slope, plus 5 over 2, 2.5 is the y-intercept. Isn't it the same freaking line, right? Like it should be. If I find it graphically, it better be the same thing algebraically. Right? 2 different ways to kind of do it.
You write the very first step.
So the reason I put this little line here, and that's just me, you'll never see anybody else do this, is because from this step to this step, did we do any algebra? No, we did something really strange. We switched the x and y. We never do that unless we're finding the inverse function. So I put the little line to say, this is what it was originally, This is the inverse function now. That little line is kind of like my dividing line. Do you need it there? No. I just kind of do it for myself to tell me that I've done something weird from here to here. So at the end here, actually, what can I put in place of y? Careful. No. F of x is that. This will be f inverse x. Okay, maybe.
When you automatically know, like, where the y-intercept is with the -5, you automatically know to switch the sign to find the inverse.
Yeah, it's got to be symmetric here. So the interesting thing about y-intercepts, they become x-intercepts for the other guy, don't they? Because they got to switch around this line. So whatever, if it would have been here, it would have been there.
Oh,
It's got to switch.
okay.
So you see that? From here, it went to there. Directly switched across that line. Okay. Now you guys start to realize why I was trying to rush through the earlier chapters, because I know I wanted to slow down here, but we'll see what happens here.
Speed back up, catch up.
Yeah, exactly. So here's an example of a problem I'd love to do.
Here's what?
An example of a problem that I love to give.
Oh, something that you love. Oh.
Yeah, I know. With me? We haven't seen a function like this ever. What would the function look like? I don't know. But I know what the graph looks like, and I can find the inverse of this function visually. How do I do that? Yeah. What points does f go through? This is f. What points does it go through?
-4, -4.
-4, -4.
-1, -2. 3, 0.
0, 3. And 3, 4, right? So what's the inverse function going to go through? -4, -4. Oh, crap. Get away. And -2, -1. 3, 0. 4, 3. All right. So -4, -4. They agree there. Because if you realize that's actually on the y equals x line. Y equals x. All right, so that's where they kind of meet at the mirror. -2, -1. That's the mirror image there. 3, 0. And 4, 3. So now watch what's interesting here. Isn't that symmetric about? Let you look at that for a minute. Looks like we're in chemistry class now. All right. This is the double helix. Twine's right. So it's always going to have to be a reflection around that y equals x line. You can't do the same thing we did here because we don't even know what the function is, but so we can only do a visual inverse. That's all I would ask for there. I'd say graph the inverse. So if that's f, this is f inverse. Okay, cool. All right, so what about what about this? Try to do that. See how far you can get. It's exactly like what we did here. it's almost